Okay. All right. We hope that's not recorded. Um, so we'll stop talking about teachers beating students, and teachers beating athletes. Um, Stuart, we'll say hi to you. This is Sammy.
Hello, Prime Minister Adam Sutler. Edna misses you.
Whoa. I don't know what that was, but that sounded like she really misses you. So we'll get going. Okay. Let's get started. We do have a decent amount of material to cover. It's and some that's easy, some that's new. This one should be fairly easy for us. It says write an equation for a line. Tangent to the function f of x is 1 minus sine of x at x equals pi over 6. So if I want to write an equation for a line that's tangent, I have to find two things. Number one, I have to find my slope. And second of all, I have to find my point on my line. It's on the bottom of your page from yesterday. Can somebody tell me uh, the x value for my coordinate? Pi over 6. How would I figure out the y value of that coordinate? I would plug it in. I'm going to take my pi over 6 and I'm going to plug it in there. So I'm working in radians in this situation. If we plug in pi over 6, we get 1 minus the sine of pi over 6. If you look at that trig sheet that I gave you yesterday, or if you just simply on your calculator try sine of pi over 6, you'll realize that the sine of pi over 6 is 1/2. So 1 minus 1/2 is 1/2. So we have two coordinates, pi over 6 and 1 over 2. X and y coordinate taken care of. Everybody with me? Now we need a slope. How would we find a slope? Derive it. Take the derivative. We need to be able to find the derivative of this. The derivative tells us the instantaneous rate of change, or the instantaneous slope at any given point. So if I want to know the slope, I have to know what the rate of change of this function is at time pi over 6, or at x equals pi over 6. So let's derive this thing. F prime of x is equal to negative cosine. Derivative of 1 is 0. Derivative of sine of x is cosine of x. So you got negative cosine of x. So if the derivative is negative cosine of x, how would I figure out the slope at that point? Plug pi over 6 in for x and see what I get. So f prime of pi over 6 is equal to negative cosine of pi over 6. The cosine of pi over 6 is the square root of 3 over 2. Anybody try on your calculator? Did you get 0.866? Yeah, so that converts to negative square root of 3 over 2. We could just write negative 0.866. I think you guys would probably rather work with the decimal. We'll forget right now for about expressing in perfect radical form, because we also have a pi over 6 we have to mess with. So we're going to need decimals here. So we'll say that the slope is negative 0.866, which is approximately equal to the negative square root of 3 over 2 if you were to look at your chart. So that's where we get that. We might as well come up with a decimal for pi over 6 as well, seeing how we're going to have to use it. So if I take pi and divide it by 6, I get 0.52. So in order to find the equation for the line, I have y equals mx plus b. My y value is 0.5. My m value is negative 0.866. My x value is 0.52 plus b. Negative 0.866 times 0.52. We'll add that over to the other side. 0.5 plus 0.450 is 0.95. So about 0.95. So the equation for my line is y equals negative 0.866 plus 0.95. Yes? Like that matters. Ooh, trash talk. Jody. I pity the fool who competes with me after school. You want a mass showdown? Is that what you want? $5. Any questions how we any questions how we came up with the equation for this line? If we were to graph it, I would encourage you to that you would graph it, make sure that it's tangent on your calculator. Let's flip over to the next side. Okay. Um, it says prove that d over dx cosecant of x is equal to negative cosecant of x cotangent of x. So we're going to do just one basic proof here. It's not very difficult. What does d over dx mean? The derivative with respect to x. So x is our variable that we're working with. We want to find the derivative of that. Stupid Luke. Okay, let him be. In order to prove that, I'm going to use what I know about the derivative of sine of x, okay? I'm going to rewrite this. I'm going to say we're actually trying to find d over dx of 1 over sine of x. Right? I could rewrite cosecant as 1 over sine. If I want to take the derivative of 1 over sine, what rule do I have to use? The quotient rule. So let's use the quotient rule. No, it's nice and easy. I take the derivative of the top, which is 0, times the bottom left alone, minus the derivative of the bottom times the top left alone. All over what? So sine squared of x. What does the top come out to? Negative cosine of x over sine squared of x. Somehow we have to make negative cosine of x over sine squared of x look like negative cosecant cotangent. Very good, Sean. Here's what Sean says. He says that we should do this. Sean says do negative cosine of x over sine of x times 1 over sine of x. So all Sean did is he split it up into two pieces. What's negative cosine over sine? Cotangent. What is 1 over sine? Cosecant. So you have a negative cosecant I've just memorized those. I think that the best sheet to look at, I don't know if somebody else have this sheet right here is probably the most useful sheet you guys will use from your trigonometry stuff. So this is the one I would encourage you to use. Uh, about 1 over sine over cosine. Yep. So the 1 over sine is cosecant, right? I have a negative, and cosine over sine is cotangent. So what we've done is we've shown that if you take the derivative of that, you do get that. So we just played around with a couple terms. Question? Negative is there. Other questions? Once, twice, thrice. Okay. Um, last piece, I don't intend for this to be extremely difficult. So we're going to do some of the easier problems here. But this is something you very, very, very well may encounter. And this is a section where they introduce the concept of limits for various reasons of certain trigonometric functions. The background behind this is difficult. And when I taught previous calculus courses, we proved how we came up with both of these. And it took a class period for each one. We're not going to do that. I'm just going to show you guys. If you were to graph this, sine of theta over theta, here's the picture of the graph that you get. It goes like this. Except it's discontinuous at one spot. Does anybody know where it would be discontinuous at? 0. You can't put 0 in the denominator, but at 0 it approaches 1. The limit of theta approaching 0 of sine of theta over theta is equal to 1. And we could prove that to you, but we would have to use something called the sandwich theorem, which we've left out. I'd be happy to revisit the sandwich theorem. It's very cool, but we would have to wait to make sure we had enough time to get through the rest of our stuff in this course. So I want to wait on that. Second one, cosine of theta minus 1 over theta happens to be 0. So if you want to see those proofs, you can look in your book, but those are identities that we do need to keep in mind. You can't have 0 in the denominator, you're right. Just like you can't have 0 in the denominator here. So it's a limit that you would have to prove through various means. So I'm going to show you how to work with a couple that are a little bit kind of tricky, okay? I'm going to write it just a little bit bigger so I can see it. The limit as theta approaches 0 of sine of 2 theta over theta. Now, when you get to these problems, we want to evaluate this. And this isn't too tough, but you got to be able to think about it right, okay? Now, this looks very similar to what I have up here, does it not? What's different about it? There's a 2 in front of that theta right here. There I don't have one. Well, I'm going to do something, okay? I'm going to multiply the expression by this. I'm going to multiply it by 2 over 2. Can I do that? Yeah. If I multiply it by 2 over 2, watch what I get. I now get the limit as theta approaches 0 of 2 times the sine of 2 theta over 2 theta. It helps us a lot. We can't cross them out. We can't cross them out. But this, you guys, it doesn't matter whether it's 2 theta or 9 theta or 20 theta. Either way, it's the sine of an angle divided by the angle. Just like up here, look at what I have. The sine of an angle divided by an angle. Here, sine of an angle divided by that same angle. So the limit of this is it's just 2. The limit of this is 1. See? The limit of this is 1. We just said the limit of this is 1, correct? Times 2. So watch again. You'll get it even better the second time. Okay, Ashley is right. It's 3/5, but if you see this on a test, you have to show it appropriately. limit as theta approaches 0 of the sine of 3 theta divided by 5 theta. Now, what number would I need in the denominator? I need a 3. And if I multiply the denominator by 3, I have to multiply the numerator. So 3 times 3. Well, now that just looks just a little bit different. The limit as theta approaches 0 of, no, because watch what I'm going to do. All I'm going to do is I'm going to switch the 3 and the 5. 3 over 5 times sine of 3 theta over 3 theta. Okay, good question, Morgan. You can't choose the 5 because you can't get the 5 on the inside there. You can't just factor a 3 out because sine is operating on that, so we can't just remove that. That's why we choose to work with the bottom. Okay? It is just the, so you get 3/5 times 1 is 3/5. So that's what you would need to show. So there's a couple stairs out there. Let me try once more. We had this original one. We want a 3 down here, so I multiply by 3 over 3. Then I just switch the 5 and the 3, okay? I maintain my property of equality through multiplication. So now instead of a 3/3, I have a 3/5. Instead of a 3/5, I have a 3/3. Because the limit of that is 1. We know that limit. We don't know that limit. We know that that limit is 1. We say by this piece right up here that if you take the sine of something and divide it by that same something, sine of something divided by the same something, you're going to get 1. So I have my 3/5 times my 1. Yep. The 2 theta doesn't come on the bottom until I multiply the top and the bottom by 2. So I start out like this, sine of 2 theta over theta, and I say I need a 2 in the denominator. So I multiply the top and bottom by 2. So the 2 gets absorbed in the denominator. The 2 up top is right out here, like a 2 over 1. Okay, 2 more. This one works out very well. But please just change a little part of it, okay? Please put a 2 in front there. I changed the problem, everybody, to cosine of theta minus 1 over 2 sine of theta. I just want to change it just a little bit. And you guys, these problems model exactly what you see in your homework. I'm trying to encourage my pre-calculus class, and when they have questions, please, if you're at home, if you're here, ask me. But if you're at home, look at your notes. I designed the notes to hopefully carry you through hopefully exactly what you see. So with that said, notice what I have here. I have a cosine of theta minus 1, and I have a 2 sine of theta on the bottom. Well, in order to know the limit of that cosine of theta minus 1, I would need a theta in the denominator, right? So instead of multiplying by a number, let's multiply the denominator by a variable. If I multiply the bottom by theta, what would I have to multiply the top by? Theta. Now, watch what's going to happen here, okay? This 2 means no, never mind to me. It's not sitting near a theta. It's just like a 1/2. Everything's multiplied by 1/2. So this limit is actually the limit as theta approaches 0 of, I'm going to write as 1/2 times. Now, I'm going to swap something in the rest of this expression. Anybody know what I want to swap with sine of theta? Theta. So this is all multiplication. I'm going to swap these two. So I'm going to have the cosine of theta minus 1 over theta times theta over now. We have, look at this. This looks very similar, doesn't it? Very similar to this one. It's just the reciprocal, right? So anybody want to guess what the limit of this is? The reciprocal, which is just 1. Reciprocal of 1 is 1. Okay, I have the 1/2 in front. What is the limit as theta approaches 0 of cosine theta minus 1 over theta? 0. So I get 0. A very good chance that they will always be 0. By that. And one more. Please change the problem. We're going to change it to sine of 2x. Sine of 2x. Okay. When I wrote the problem, I did it in my head, and I was sure it was going to work out. It doesn't quite work out the other way. It should work out now. Take a chance. Take a chance. Anybody know that's not Take a Chance on Me by ABBA? My daughter loves it. When I come home every night, Daddy, can we play Mamma Mia? And can we play Take a Chance on Me? Okay. I'll look into it. Why can't we just plug in 0 and define this? You would get 0 in the denominator because sine of 2 times 0 would be 0. The sine of 0 is 0. So we can't plug in 0 in this situation. So we need to work this out a little bit differently. So I'm going to use some of my trig identities. What is cotangent the same as? Also written as cosine over sine. So I'm going to rewrite this. Cosine of 5x over sine of 5x divided by sine of 2x over 1. And before we go any further, I just realized as I'm doing this problem, this limit does not exist either. So, sorry. Here's how I know. If you plug in 0 for, I'll show you. If you plug in 0 for cotangent, cotangent is undefined at 0, so this limit doesn't exist. I wrote a stupid problem. All right, so I won't put that problem on your assignment. All right. Somebody want to say bye, Stuart?
Later, Stuart.
That was Sean. Later, kid. Bye.